So now let's build the margin error. Here's our data set twice. And this is a boundary line. And these are the margins. Now there's a difference between the model in the left and the model in the right. The model in the left has a very large margin, and the model in the right has a very small margin. Recall that the margin is the distance between the two lines. And we want to turn this margin into an error that we can minimize using gradient descent. We're going to cook up a function that gives us a small error for the large margin case and a large error for the small margin case. This is because we want to punish small margins, as our goal is to obtain a model that has as large a margin as possible. And you'll be surprised how simple this is. Here we have our line with the two other boundary lines, and the margin is the distance between the two outside lines. Our equation is the line wx plus b equals 0. And the two dotted lines have equations wx plus b equals 1 and wx plus b equals minus 1. That is just the way we pick them. And so the margin, and we'll see this development in the instructor comments, is simply 2 divided by the norm of the vector w. Let's remember that the norm of w is the square root of the sum of the squares of the components of the vector, which are w1 and w2. So for this error, let's find something that gives us a large value if the margin is small and a small value if the margin is large. Well, simple. The norm of w appears in the denominator, so if we take the norm of w, that grows inversely proportional to the margin. Nice, right? As a matter of fact, since I don't like dealing with square roots, let's take the norm of w squared, which is actually the sum of the squares of the components of the vector w. In this case, it's w1 squared plus w2 squared. And as we've seen, since w appears here in the denominator, then a large margin gives us a small error, and a small margin gives us a large error. That is exactly what we wanted. So to clarify things, here's an example. Let's say w is a vector 3, 4, and our bias is 1. So our equation of the form w1x1 plus w2x2 plus b equals 0 is going to be 3x1 plus 4x2 plus 1 equals 0. And that's our main line. And here's the line with its two companions, the one that gives the equation 3x1 plus 4x2 plus 1 equals 1, and the one that gives 3x1 plus 4x2 plus 1 equals minus 1. So now the error is the norm of w squared, which is 3 squared plus 4 squared, which gives us an error of 25. And the margin is 2 divided by the norm of w, and the norm of w is the square root of 25, which is 5. So the margin is 2 over 5, and the error is 25. Let's remember these two numbers, error 25 and margin 2 over 5. Now let's look at a very similar example, except instead of 3, 4, 1, our weights are going to be 6, 8, and 2. So our line is going to have the equation 6x1 plus 8x2 plus 2 equals 0. And if you notice, that equation is the same as before, except multiplied by 2. So it gives us the same boundary line, because when 3x1 plus 4x2 plus 1 is 0, then 6x1 plus 8x2 plus 2 is also 0. But now our dotted lines are closer to each other because now the values change. Before we had 3x1 plus 4x2 plus 1 equals 1. And now we have that twice of that equals 1, which means 3x1 plus 4x2 plus 1 is actually a half, which means the line is much closer. It's actually half the distance as before. And the same thing happens with the line below. And our error is the square of the norm of this vector, which is 6 squared plus 8 squared, which is 100. And our distance is going to be 2 over the norm of w, which is 2 over 10. That is the same as 1/5. So this is smaller than the previous margin of 2 over 5. So this is interesting. Two models give us the same boundary line, but one of them gives us a larger margin than the other one. So here's a summary for our last example. We have our large margin, our margin of 2 over 5, that gives us a small error of 25. And our small margin of 2 over 10, which is 1/5, gives us a larger error of 100. So that is precisely the margin error. It's just the norm of the vector w squared, which if you think about it, it is the exact same error that is given by the regularization term in L2 regularization. Nice, isn't it?